All right. So we left off last class on Monday. We talked about calculating means, calculating variances. We were looking at data sets where every observation represented like one person, one country, and we were thinking about, everything should be equally weighted, right? There's a lot of situations where we probably don't want to equally weight the data that we have, right? So maybe this is something like we want to find the average income in the US, okay? So let's say I want to find the average income in the US, but all I have is income data for every state. So I've got like the average income in California, the average income in Indiana, so on and so forth. Well, I don't want to simply add them up and divide by 50 because I know that each income measure represents a different number of people. Like the average income in Delaware represents way fewer people than the average income from California, right? So I want to try to weight these, right? So, in that example, it probably makes sense that our weights are going to be something like the population or the working age, population in those states. But how exactly do we use those weights to then come up with our weighted mean? Okay. So another example is, maybe something like I want to find the average fast food sales or a burger fast food sales. And I've got, the average sales at a McDonald's establishment, but that just represents the average at one establishment. And I know that represents a way higher number of stores than the average sales from, Jim's Burger Shack or Berkey's or, choose your one location kind of fast food place. Right? I used to like that example a little more, but I think I like the income one across states. It makes a little more sense. So what we're going to do is we're going to go through and we have this group data, right? Like in the income data, I can't see every person's income. I'm only seeing income by each state. So I'll take each state's income, multiply it by the weight, which is like the working age population in that state. And I'll do that for every single group that I have or every single state that I have, and then add them all up. That'll kind of represent my numerator there. And then my denominator is going to just be, well, what's the sum of my weights, right? So adding up the working age population across every single state, that represents my denominator. Okay. So let me see here. I've got kind of the steps written out. What we're going to do is go through every single observation, take each group's value, multiply it by its weight, then add them all up. We're then going to add up all the weights to get our denominator. And now we just have two values, right? Divide the sum of the products by the sum of the weights. So another way of thinking about this is, and I'll write that equation down again. So if you were trying to write that down. This is going to represent our weighted mean. Okay. So I want to kind of try to relate this to what we were doing before. So if I had just a regular mean, that was kind of just adding up all the X values, dividing by the number of observations that I had, right? So there's no real way that we denote the difference between a mean and a weighted mean. It's just that it depends on what type of data we have. Okay? So another way we said that we could write the regular mean was if I'm dividing everything by n, it's really the same as multiplying each observation by 1 over n and then adding them all up. So we were saying like every observation was getting weighted by the same amount. It was representing 1 out of the total number of observations. But with a weighted mean, we can also rewrite it to kind of think about what our weights are. Our weights are no longer going to be 1 over n. Here we can kind of pull out the weight for the first group, divided by the sum of the weights, times that first group's value for x. We would then add to that the second group's weight, divided by the sum of the weights, times that group's value for x, all the way to the very last group. Right? So it's a really similar thing. It's just instead of weighting every observation by 1 over n, we're weighting it by, well, think about the income example. It's how many people in that state out of the total number of people in the US, right? So we're really weighting each observation by whatever proportion of the overall observations that group represents, right? Or that group's weight. So we're going to break this down to make a little more sense. And I'll show you an example in a second after we work through some data. I'll kind of give you a weighted grade example, and we can kind of think about what that would look like. And sometimes this way, once we plug the numbers in, is intuitively makes a little bit more sense to some people. Okay. So with this in mind, how would we actually apply this to an actual group data set? Right? So the census, right, is done every 10 years, and it gets supposedly, I mean, its goal is to obtain data from every single person in the US. Right? Now here, the US Census, it has a smaller subset of that will then give, you can actually request the data, but it has to be broken down by characteristics. So I can't observe the 108,000 male observations here with 108,000 different incomes. I can only get the average income by different gender kind of race combinations. Now, obviously, this is like simplistic kind of list of race. This is what the census collects. There's obviously, we could break this down to more categories and have a much lengthier discussion about, what race is. But here, we'll just take what the census has as given, right? So these are our 4 groups. So how could I find the overall mean income for men here? Well, I've got 4 groups. I'll go through each group. We're going to use the number of people that were in the original data before it was grouped, right? So there's 73,000 individuals classified as white, 6,000 as Asian, so on and so forth, right? So I'll take the first group. Their weight will be 73,000 multiplied by the value for this X variable income I'm interested in. So 73,000 times 59,000. And then add to that the next group's weight, 11,000 times 38,000 plus 6,000 times 60 plus 17 times 36. That represents my numerator. I'm just adding up all of the values for X from these groups, multiplied by that group's weight. I then will divide by the sum of my weights, which here I kind of gave you ahead of time, right? I kind of actually did that work for you, right? I just add the weights up here to get 108,000. If I write all that out, it's going to look something like this, right? I took the first group's weight, multiplied by that group's value for X, added to that the second group's weight, multiplied by that group's value for X, did that for all 4 groups. I then divided by the sum of the weights here, which if I wanted, I wanted to make sure that if I didn't give you that total, you could have found it yourself, right? But if I already had that total, the sum of the weights, I could have just plugged 108,000 down in that. Any questions on that before we I keep adding some things in here? So I could do the same thing for female income here as well. I would just have different weights and different values for X, but it'd be a really similar procedure, right? What if I wanted to use this data to find the average income in the US regardless of gender? I just want to find the average income in the US. It'd be a very similar process. It would just be now, instead of 4 groups, I've got 8, right? So I would, do the same thing, take each male group weight times its value for X. Once I add all those up, then I'll add in the first female group's weight times its value for X plus the second female group's weight times so on and so forth. Once I add all those up, I'd have my numerator. And now the sum of my weights would just be the sum of the male weights as well as the sum of the female weights. So it would just be a lengthier process, right? If this is the only data that I had. Okay. So you'll notice that, if I were to treat this like a regular mean, for males here, and I think I've got, yeah, there we go. That if we could reproduce find this mean, we could also do the same thing for female income. But you'll notice if I was to treat this like a regular mean, where I just add up these 4 values and divide by 4, I've got what? 2 that are close to 60 and 2 that are just, a little bit under 40,000. So I actually would end up with a mean, if I treated this like it wasn't group data, probably around 48, 49,000. However, that's an incorrect measure because this value of 59, it represents way more people than any of these other groups, right? So it should be influencing that weighted mean a lot more, right? So if I instead treat this correctly like a weighted mean because it's group data, this 59,000 is going to influence that weighted mean the most, which is why it pulls it up to be about 53,000, right? So it's not going to be as low as 48 or 49 like it would be if we treated this like it wasn't group data, just a regular mean, because this value of 59,000 is going to be carrying a lot more weight than any of these other low values because the group sizes are just much smaller. Same kind of idea for the female data as well, right? It's going to be influenced more by this 34,000 than it is these from any of these other values from these other groups. Okay. Any questions over anything I said there, or just questions in general about this approach? Yeah. Mhm. So you could, but it would be like if I actually wanted you to do that, and I think this would make a lot more sense. So let's say I have this. Let me open up Excel here. I'll paste it in here so we can see this. I would probably have organized it something like this, where get rid of this. And then like maybe I do like female, male. So that like here it makes a little more sense, right? I'll just go all the way down. Take each group's weight times its value for X plus this all the way down through all of them, right? I wouldn't probably stack the data side by side because it would make a little more sense to have it in a one like column format if I wanted you to find the overall income. Now, when I do that on the exam or something, probably not with 8 groups because that would just take quite a bit more time. But you could do it. Like I would expect that you would know how to do it. But yeah, probably not as many observations as that. Was there a follow-up question?
Only because if it was on the other side, I didn't know if like for the males we were multiplying them and then adding it with what we were multiplying for the females, or if we were just multiplying.
Yep. So you wouldn't multiply straight across, right? It would be more so like I did here. Like you would actually be kind of like stacking the data and then just going through each weight times the X value. You could also like, I'll do this later on for an example as well. But since you're asking the question, it's pretty relevant right now. What I would probably do, like what you would do by hand, or you could actually do it in Excel pretty easily if I can type. I would just create another column, right? Like stack the data and just say, okay, I'm taking each group's weight, multiplying it by that group's value for X. Then I would do that for every single observation and then add them all up. Does that answer the question?
Yeah.
Okay. Mm-hmm. Any other questions at this point? Oops, hold on. Get rid of all that. There we go. Okay. So we've got our 2 weighted means. I could also do this by region. That's another way you can request the data. So if I'm thinking here, if I'm looking at either male or female income, which region is going to influence my weighted mean the most? Yeah, the one that has the highest number of observations in it, or the South, right? About 40,000, 41,000 for females, right? So those would be the 2 categories that carry the most weight, right? Now here, there's not near as much variation across regions and income, right? Like these are all like pretty similar. Whereas when we're looking like up here, right, there's much larger ranges that we were seeing across racial categories as opposed to across regions. So it won't be as evident that that group is carrying more weight, but that will be the group that is influencing that weighted mean the most, would be the South there. And I think at one point I was using this for eye clickers and I forgot to take out the A, B, C, D there. Okay. Before we go to weighted variance, let me give you another maybe useful application of weighted means. Right? So I'll kind of simplify this. So let's do homeworks, exam, and we'll do project. Right. So we've got the weight. Right, in different classes, maybe you're told, homeworks are going to account for 20% of your grade. The exam will be 30, and then we have this huge class project that's 50% of your total grade. Right. You then have at the end of the semester, okay, what was my score in these different things? So maybe I don't know. Let's say this person did really poorly, but they did really well in that project. Right? So this is a 9. You actually would find the weighted mean to calculate your grade in the class, right? Because you don't want to simply add these up and divide by 3 because, this isn't going to carry as much weight as, the 40 doesn't carry near as much weight as the 90. So if you just add them up and divide by 3, you're not going to get your grade because you're treating them all equally. So what do? You go through, you take each category's weight, multiply it by the score you got in that category, add the next category's weight times the score you got in that category, next category's weight times what you got there. And then you would divide by the sum of your weights, which if we're doing a grade example, what should the sum of the weights likely be? These are representing percentages. Hopefully the instructor set it up so that they add up to 100%, right? They might use points or something that might be a little different, but it'd be the same idea, right? So another way of thinking about this, so this is our weighted mean. I'm just going to write this out a little bit differently, right? Remember I said we could rearrange earlier and think about the weighted mean in this format? So I could think about the first category is 20 out of 100%. So that's how much that score is going to get weighted by. And then add to that, the next category is 30 out of 100%, multiplied by whatever grade I got in that category. And then the final one, the project accounts for 50 out of the 100% of your score possible times the score you got in that project. So it's just a different way of thinking about calculating the mean. I think this one's probably a little more effective and a easier way to do it. But sometimes this one kind of lines up more with people's thinking, right? Like, oh yeah, I'm like weighting it by 20 and then have to divide by some of the weights. No, what you're really saying is it represents 20 out of the 100 possible points. And so even if an instructor did something like where the weights don't add up to 100, so maybe there's like, a bunch of other categories and the total number of points is 400. Well, here it would still be like, okay, well, this is 20 out of the 400 points is my weight. I say it doesn't really matter which way, whichever one of these methods kind of is easiest for you or connects most with you, that's the way you can think about it. It's just a slightly different way of thinking or kind of visualizing what this weighted mean is. Okay. Any questions on that? All right, so if we can do a weighted mean, we can also do a weighted variance. Right? Now it's going to tell us something slightly different than the regular variance did, but let's try to actually just build this out. So we can do this weighted variance for group data. And before I show it to you, let's see if we can kind of figure out exactly what it's going to look like. Right? I think maybe me writing it out will help a little bit. So our old variance, right, without group data, was we were adding up the deviations from the mean squared and then dividing by the total number of observations. And then if it was sample data, we said we would just divide by n-1. Right? There was a slight difference there. Okay. So the variance was giving us some like the mean was telling us the average value for x. The variance was telling us like the average deviation from this middle part of the data, right? Or the average deviation from the mean squared. So if we're doing a weighted variance, we still want to pick up this like average deviation from the mean squared. However, we know that each deviation from the mean from each group represents a different number of people. So we'll multiply it by the weight. We'll take each group's deviation from the mean squared, but now we'll have one more step, which is multiply it by the weight for that group as well. And then just like the mean, we'll divide by the sum of our weights here. Now, if it was sample data, we would do the exact same thing, but we'll divide by the sum of the weights minus 1. Okay. It's a little bit different, but a similar idea. Okay. Now, one thing that I'll kind of mention here, and I think I show it to you in the slides, is let's think about the income example. If I really did have every working aged person in each state, and that's what I was using as my weights, when I added up all my weights across all 50 groups or 50 states, what would the sum of those weights actually represent? So if the weights were the number of working age people in each state, when I add those all up, I would get what? Just the total number of working age people in the US, right? It's every single, I have added up across every state. And so really what that would represent is the total number of observations in my population. So the sum of our weights, right? Remember, we see group data. Well, this group data at one point was individual level data. So there is some total number of observations that was in that population before it was grouped. But each one of those observations should only be getting counted like once in each state. So when I add those weights up, or I add up those populations, it represents the total number of observations that existed in this data set that I can't see, right? Before it was grouped and then given to me, okay? So we can write the sum of the weights in here, but sometimes if you were like told ahead of time, if you knew the total number of observations that was in the data before it was grouped, you could actually just plug that in. You wouldn't even have to add up the weights because they should be the same exact thing, okay? So I've got that here, right? Kind of two ways of thinking about this equation. They're really saying the same thing. More often than not, we're going to have to add the weights up ourselves. But, if I go back here, sometimes some of the weights is already given to us, right? And so we could just plug that in if we had that. But kind of depends on what information we're given. Okay. Any other questions on that before we keep moving? Okay. So how would I find this weighted variance? So I went back to that income data that was broken down by race, and I just pulled out the male just so we didn't have as much going on the screen. And what I would do is go through each group, take their value for X, so 59,000, subtract the mean. We found the weighted mean was around 53,000. I don't remember the exact number. So 59,000 minus 53,000 squared, and then multiply it by the weight for that group, which was 73,000. Write that number down. Go to the next group, 38,000 minus that mean of 53,000 squared, multiplied by about what, 11,800 was the weight for that group. Once I do this for every single group, I'll then add them all up. That would represent my numerator. And then I would divide them by the sum of the weights here. And that would give me that 94,000 weighted variance. Okay. So kind of breaking this down a little bit by step. And then I'll also show you an example of this in Excel. Yeah. Yeah. So you're right. When you're right. I'm actually speaking lazily, right? Instead of, I'm not subtracting the regular mean when I'm finding the weighted variance, I'm subtracting the weighted mean. Yeah. Anytime you have group data and you have to do a weighted variance, you should also be using the weighted mean. Unless you were somehow like, no, not even if you were given what the other mean was, you would still want to use the weighted mean. And I'll explain why in a second, because this variance tells us something a little bit different than we were calculating a variance from non-group data. All right, so I'll show you, I want to break this down a little bit more. So I'm going to copy, actually, can I just get this? Yeah, I'm just going to copy the female data over here. And we're going to go to Excel. I'll show you. First of all, I'll zoom in so we can actually see what I'm doing. When you copy and paste something in Excel, especially if you're doing this from like PowerPoint, and maybe some of you already know this, but this is like I think a pain if you don't. You usually have multiple paste options. So like this first one, notice it's like trying to put the formatting from PowerPoint and it's like ridiculous, right? It's like I've got to change all the columns around and it's but if I choose this second option, it's always whatever the default formatting is that you have in Excel. So I think like usually it's just like 12 point Times New Roman or something like that. And it doesn't change the width of the columns or rows or anything. And so it's kind of a little bit easier to deal with sometimes. So if you right click to paste, instead of just hitting like here. So if I use the shortcuts like Control V or Control C, then Control V, it keeps the formatting of where I'm copying it from. Well, that's annoying. So I'm going to right click and choose this second option, which is match destination formatting, which is just this default. That's kind of a nice, just a little tip or trick. So I'm going to show you kind of what if I want to do this weighted mean. And I think there's some built-in weighted mean functions like weighted average or something, but I want to break this down step by step. So if I want to do the weighted mean, I basically could use Excel to be my calculator and save myself, especially with numbers this large. You saw some of those intermediate values, they were very big, right? Like 2 million or 20, not even more than 2 million. So it's kind of annoying to deal with numbers that large. So it's a little bit easier to do in Excel. So I'm first going to find my numerator, which is just taking each group's weight, multiplying it by that group's value for X, and then add in the next group's weight times its value for X, add in the next group's weight times its value for X, and then add in the final group's weight times its value for X. That gives me that numerator, right? I don't have to type all these numbers into my calculator, right, that are very large. I also have to do what? Divide by, what should I be dividing by to get my weighted mean? The sum of nobody. What should I be dividing by? The sum of my weights. I know this is the variance, but right, we're dividing by the sum of our weights here. Okay. So what's one way I can do that in Excel? Well, I could like click this, plus this, or I showed you this function when we were working in Excel before, which is just the sum function. It makes my life easier. I don't have to type in as many plus signs because all I have to do here is select those weights, right? And it'll add them all up for me. So this is also one thing I wanted to show you is that when we're doing things in Excel, a lot of the times in class or even the examples that I worked through, I'm going to break things down step by step because I think it's like easier or will make the whatever we're working on a little bit more digestible or make more sense to you. That doesn't mean you can't do it all in one cell, right? So I'm about to do something in a second where I break it down to parts, but you really could do it all in one cell. It's just that it becomes kind of a long equation. Sometimes it's easier to see the intermediate steps, but notice here, I can do a bunch of math as well as use built-in formulas. And then whatever number that formula gets, I can also use that in an equation. I can do all of this in one cell. I can use multiple built-in formulas. So I could use the sum function twice. We'll kind of see as we progress, I could do, any combination of built-in functions or formulas. So here I just did this all in one line and I can reproduce that weighted mean. Okay. Any questions on anything? I want to make sure I'm not moving too quick here. Okay, so I've got my weighted mean. I'm then going to go through and break down the steps and calculate this weighted variance. So the first thing I'm going to do, right, and that little caret, that's the thing that's above the 6, this represents taking something to a power. So this to the second power is like squaring it. Right? So what I'm going to do here is for every single group, I'm going to take their weight, and I'm just going to multiply that by their value for x minus the mean, and then that caret 2 says to the second power, or squaring it. Okay, so I'm just going to use it, use Excel to be my calculator here. Now, if I copy this down, so I want to do this for the next 3 groups, what's a problem going to be? So, okay, it looks like it's working, right? Oh, but remember, it updates all of my cell references. So it's also updating that cell reference for the weighted mean. So what do I want to do there? Freeze that cell reference, right? Because I always, every group, I need to subtract the same weighted mean. Okay. So now when I copy this down, this should give me my correct values. Okay. Now, one thing here is, if you're looking at this, what the hell, why is there a letter in my number, right? So this is basically when numbers get too large or too small in Excel, it defaults to displaying it in scientific format, scientific formula format. So what this is really saying is e to whatever number, if it's a positive number, it means move the decimal that many places to the right. So this is really saying take 2.42906, move the decimal 11 places to the right, and that's the actual number in this cell. It's just that's too long of a number for us to show you without changing the width of the column. Right? So if you have a negative value like e to the negative 11, that would mean take the decimal and move it 11 places to the left. And we'll see this kind of start popping up when we deal with some probability stuff here next week. Okay. So I've got the deviation squared times the weight for each group. So then I'm going to just add those up. I'm going to type out kind of some labels because I'll post this to Canvas after today's class, so that what we did last class, I think I called it like Indiana weather in class work. I'll probably call this one like weighted variance in class work. Okay. I'm also going to find the sum of my weights, and then I'm going to use those two. That's my numerator and my denominator to find the weighted variance. Right? So here, I'm going to use that sum function again. Right? I'm just going to add up all the deviations from the mean squared times their weights. I'm then going to use the sum function again, add up my weights here. Now I've got my numerator and my denominator, and I should be able to reproduce my weighted variance. Now, instead of selecting the cells, you can also use the arrows. Notice it's changing the cell reference. So I wanted the one that was right here. Okay. And now I've got that weighted variance of about 15 million. Okay. Any questions kind of over anything here? This isn't on like the current Excel assignment. This is just me using Excel to kind of show you some, another way of thinking about the weighted variance. So we reproduce this value of 15,000. Okay, and then up here, I kind of walk through the male variance. So here, what can I say using this statistic of weighted variance? So if this was like not group data, and I found the variance on male income and female income, well, a higher variance just tells me that there's more variation in male income, right, across every male in my data set. Here, the variance tells me something a little bit different, because it's not variation in male income that the weighted variance represents. It's the variation that exists in male income across races, right? The variation that I'm picking up is from different racial groups. So the weighted variance represents variation in this X variable with respect to whatever my groups are. So here, there's more variation across racial categories in male income than the female variation that exists across racial categories, or the variation that exists in female income across racial categories. Right? So it's telling me something just a little bit different, right? It's with respect to the group that I'm picking up variation in this variable. So for instance, with the region, I could recreate these values, and I'm not going to do that in class. If you wanted some additional practice, like here's some numbers you could go through and try to reproduce this. But here I also see that there's more variation in male income, right? A higher weighted variance with respect to the region. So male income varies more across regions than female income does. Okay. So it's a slightly different interpretation, right? And it would, be a little more useful in different applications than just a regular variance, or less useful in some applications or in scenarios. So we've got this weighted variance, kind of tells us, something about the variation that exists in respect to whatever our groups are. What is the lowest I could ever see my weighted variance be? What was the lowest we said we could ever see the variance be? Just a regular variance. 0, right? So if the lowest my weighted variance could ever be is 0, what would that data set look like? Like in respect to income and race here, if I had a weighted variance of 0, what would I need to see? Every racial category would have exactly the same income. There would be no variation with respect to male income across any racial category, which would mean that every single racial category had the exact same average income measure. So a weighted variance of 0 in respect to income here, is a good thing. like it's too bad we don't see a weighted variance of 0 here, right? We wouldn't want it, to be completely equitable, right, across racial categories. We would hope to see a weighted variance closer to 0. In fact, last class, something I wish I would have thought of, because I forgot that this exists. You could go to the Census Bureau's website. You could get this data, but they have it at different points in time. So one thing I think I'll try to introduce in the class, just because I'm curious about it, and I think it'd be worthwhile to kind of show you the usefulness of what we're doing. Over time, if I got this income data and I calculated the weighted variance, what should I hope is happening to that weighted variance over the last 40 years? That it's going down, right? My intuition would be that it is, but I don't know. I hope it is. I guess maybe is a better way of saying that, right? So you could actually go out and grab that data and see that, and that's a really useful application of this weighted variance, right? Hopefully we see it decreasing over time. All right, that's kind of an aside there, but that's how we could use this weighted variance. Where we at? Okay. So one more thing that I want to go over today, and this is going to be useful. I've had a couple questions that people were working through the Connect homework, and they got kind of stumped on one that looked very similar to this. And it's because we haven't covered it in class. I said the last couple of questions, we'll make sure we cover that material on Friday. So this is some of what I was referencing. So let's say that I've got some group data, and it was kind of like the group data we were using to create histograms, right? We put a continuous variable into bins, and then we have the frequencies, and that's all I can observe. So there was, I believe, 65 people who had some satisfaction rating of a product. The company then kind of put the data out, with the frequencies of these different bins, right? It forced it to be group data by forcing it into bins. It doesn't want anyone else to see each individual's response. So this is all we can see. Well, if I was curious about the mean of this satisfaction rating, I'd have to find a weighted mean. My weights are just going to be the frequencies. That makes sense, right? But what am I going to use for the values of X? Because I've got a range of values. So if I have these ranges of values, what probably makes sense, like if I've got 36 to 38, if I can only use one value to represent that bin, what value would make sense to choose? I think someone maybe says, so 37, right? The value that's exactly in the middle of that range of values, right? Or the middle of that bin. So we'll use the midpoint or the median of these bins as our values for the X variable. And then we'll use our frequencies as our weight. So the notation I'm going to show you will look a little different, but it's really just subbing out that we're not using the actual value for X, we're using the midpoint, and our weights are going to be frequencies. Okay. So if before we go ahead and calculate it, if you had to guess, like, where's the weighted mean for this data set? Around what value? Or around what values? 42, 43, 44. And why would you think that? Well, first of all, the group or the bin that's going to carry the most weight or has the highest frequency is going to be a value of 43. So right away, that's going to be influencing it the most. From there, as we see bins on either side of that, right, the frequencies are getting smaller and smaller, so they have less impact over the weighted mean. But also, like, there's equal values like on either side of that in that middle point. So I would guess around 43. Relative to the variance measures that we had just calculated for the income data, what do you think is probably going to be true about the weighted variance for this data set? It's going to be relatively smaller or larger? If you had to guess, gun to your head. Probably shouldn't use that phrase, but if you had to guess, what would you guess here? Relatively smaller or larger than the variance we found for income? No thoughts at all. So if I'm looking here, first of all, even the range of how far away some of these values are, 37 and 49 are only going to be 6 away from that, or around 6 away from a mean of about 43. We're looking here, I mean, we had differences, 59 minus, we had 6,000, right? So right away, just the units probably make the variance smaller, but also the majority of the observations are really, really close to 43. Even the bins that have midpoints further from that mean, they don't represent near as many people as the bins really close to it. Right? So probably a relatively smaller variance if we had to guess, but we can go through and actually calculate it. So the mean will have a slightly different, formula. It's really just going to be notation here. Our weights, we're going to write as our frequencies because that's what we're using as our weights. And now we're not using an actual X value. We're using the midpoint for each one of these bins. Okay. And similar to before, I'd mentioned the sum of our weights being the number of observations. Here, the sum of our frequencies is the total number of observations that was in that original sample data that we couldn't observe, right? The original 65 ratings that were then grouped and given to us. Okay. So that's why we kind of have two different ways we can think about this weighted mean equation. Okay. We then have the variance, right? Which is similar as we did before. We're going to take the deviation from the mean. Well, now we're using our sample weighted mean, right? The deviation from that mean squared multiplied by the weight, which we're now using frequencies. And then here I put n minus 1, but I could also write that n minus 1. Remember we said, like when we were doing the sum of the weights minus 1, here, the sum of my frequencies minus 1 would be the same as n minus 1. Remember we said the sum of our frequencies when we were building that histogram. I even showed you a check. I said at this point, you should check to make sure you've got the total number of observations when you add up your frequencies, right? And so the sum of the frequencies should just be whatever the total number of observation was in that original data set that was grouped and then given to you. So any questions up to this point? We'll walk through this example here in just a second. All right, so here, if I wanted to walk through this, I've got the satisfaction rating. I'll use the midpoint of 37 times the frequency for this group, which was so 4 times 37, write that number down. Next group, 40 times 15, write that number down. I'm getting the weight or the frequency here multiplied by the midpoint for each one of these groups or each one of these bins. Once I do that, I'll add them all up. That represents my numerator. I'll then add up all my frequencies here. That should give me the total number of observations in the original data before it was grouped, or the sum of my frequencies, and I'll plug that into my denominator. So just the numbers worked out nice here. It ends up being exactly 43, right? There's probably a reason why I chose these numbers to make the math a little bit easier. Okay. Any questions on that? And sometimes this could be something where you could even save some time. Like, let's say they gave you the data and said, you know, here's the group data for the original 65 people that we asked to rate this product. Well, then you wouldn't really even have to add up the frequencies. You would already know, like, you could potentially be given that, you know, the original size of the sample was 65, in which case it would save you a little bit of work, right? Not a whole lot, but. So we've got this weighted mean of 43. We're going to use that to then calculate our weighted variance, right? So breaking it down step by step just a little bit so we can see this. I'll go through that very first observation. I'll take its first group, take the midpoint, which is 37, subtract that weighted mean of 43. So that's -6, square that, that's 36, and then multiply it by the frequency of people that were in that bin. So 4 times 36, we get 144. Go to the next group, take its midpoint of 40. 40 minus the mean of 43, -3, squared is 9, multiplied by the frequency of 15, 9 times 15, we get 135. Do that for every single group. Once I do that, add them all up. This represents that numerator, right? The sum of the deviations from the mean squared times that group's frequencies. Times that group's frequency, sorry. That's my numerator. Because the original data was sample data, I'll then divide by the sum of my frequencies. But for the sample variance, right? This here we've got a sample weighted variance. I'll divide by the sum of those frequencies -1. Okay. So relatively quite a bit smaller variance here, which just kind of makes sense based, you know, some of the things I had mentioned earlier. Okay. So we've got our weighted variance. How would I find my weighted standard deviation? Based off of how we found the standard deviation that wasn't weighted, what do you think the only other thing we need to do here is? So to go from a variance to a standard deviation, all I do is just simply take square root, right? So same kind of thing with the weighted variance, weighted standard deviation. Once I find my weighted variance, all I have to do is take the square root, and that'll give me my weighted standard deviation, right? And I know that seems kind of like an easy question, and I'll probably ask it way too many times, but I really want to like hammer this idea home because it'll become useful for a lot of things we do to like very quickly know, yeah, going from variance to standard deviation, just take the square root. Okay. No matter what scenario we're looking at, we'll look at some other types of examples too, where, you know, dealing with a variance, it's going to be a little bit different, but to go from the variance to the standard deviation, it's always just take the square root. Okay. Any questions on that before we keep going here? All right. So I've got this percentile. I think I started this with one section, but I don't know. We're going to have to finish the discussion on Monday anyways. So I think we'll just pick up with percentiles and then do some like correlation stuff on Monday. One thing I do want to mention before we get out of here. So you've got those 2 homework assignments. Hopefully you've been kind of working on those, piecing away at them. Instead of doing an online quiz today, one thing I am going to do, and I will give you a little bit of time to do it. I'm going to put the next Learn Smart up there. So it kind of goes over probabilities, which is stuff that will start on Monday, but really kind of dive into on Wednesday. So as soon as I get back to my office, I'll get that second Learn Smart post, or I call it Learn Smart. They're now called the Smart Books. Sorry. I'll get that posted and it'll be due before we start class on Wednesday. Right. So you've got quite a few days to do it. Should take 10, 15 minutes. It's just graded for completion. But you'll see that pop up there on Canvas. Okay. Have a fun, safe weekend. I'll see you guys on Monday.